こんにちは。私は Google のタヴァレス・グレッグと申します。よろしくお願いします。これは O3D のトピックなんですけど、O3D を知っている方、手を挙げてください。で、実際に体験してみました人たちを手を挙げてください。そうですか。あと、D3D かOpenGL 使ったことある人も、はい、そうですか。じゃあすみません、これから英語になっちゃいますけど、yeah, so O3D is a JavaScript API for doing hardware-accelerated 3D graphics in the web page. And the important point of that is that it's hardware-accelerated, so your users will get the acceleration advantages of their modern hardware from JavaScript. And it's also important that we mentioned that it's a JavaScript API, so you use the JavaScript built into your browser to control O3D. Another thing that's important is you can see from the images up on the screen, you can do anything you want with it. It's a low-level API, and whether you want to make games, you want to make a house configurator, you want to do data visualization, a mapping application, basically the sky's the limit. So before we go too far, I wanted to mention a few of our design goals so that you can kind of see why we made some of the decisions we made. First of all, we wanted it to be expressive. And by that, our goal was that you should be able to display fairly modern 3D graphics, things like reflections and depth of field and fancy lighting and all those things that you see in a modern game. But also we wanted it to be fast, because if it's not fast, what's the point? And so we made a system that's capable of displaying thousands of objects in the user's browser. Like I mentioned, we want it to be flexible. And by that, we didn't really want to make any assumption about what you were making. We didn't want to assume you're making a game. We didn't want to assume you're making just a 3D viewer. If you want to do 2D, that's fine. Anything you want to have fast graphics, you can use O3D for. And then finally, we wanted it to be portable. Like all web things, we wanted it to be as much as possible that you would write it in one place and it would work on everybody's browser. And so, for example, right now, O3D is implemented as a plugin. It runs in Safari, Chrome, Firefox, and IE, and it runs on Linux, Mac, and Windows. A few highlights I wanted to cover. It's entirely shader-based, kind of like OpenGLES. We have no fixed function pipeline. And that gives you access to any shader you want to write, as well as you can do things like multipass rendering to do reflections, depth of field, all those kind of things that you see on modern games. And of course, all the rendering states for blending. We load various formats. Of course, we load the web formats, JPEG and PNG or PNG. But we also load TGA because a lot of game assets are in Targa format. And we load DDS because that's the only format that supports things like cube maps, volume maps, and hardware compressed textures. We are in JavaScript, but there were certain things we decided that JavaScript is probably too slow for. One of those is animation and skinning. So we have an in-plugin system for animation and skinning, and you'll see some of that later. And another thing that came up, which is very important, is that JavaScript is got different speed on different browsers. Some browsers are very slow, some browsers are very fast. I think right now Chrome is #1, but there's a good competition going out there. Since we claim we're #1, the other browser manufacturers will try to beat us, and that makes all of the browsers faster. That being said, we have the problem that if you're going to try to write a game or something else that requires high performance, you need to count on fast JavaScript. And so our solution was we put Chrome's JavaScript, which is called V8, directly in O3D. So when you're programming O3D, you can use the normal browser, the normal JavaScript that's in your browser. But if you find that your application is too slow in certain browsers, you can choose to use the Chrome V8. And we found with some of our samples that you only have to change a couple of lines. And finally, we have a flexible way to get assets into O3D, and I'll go over that later. So one thing I wanted to go over is that the difference between an immediate and a retain mode API. I'm sure some of you have experience with those. O3D is a retain mode API, and we're going to go over why. In an immediate mode API, you issue a graphics command, and it immediately gets executed on the hardware. And so that's very flexible, but it has the problem that every time you want to draw an object, you have to issue all the commands to draw that object. So examples of those are Direct3D, OpenGL, and even in the HTML world, the HTML canvas is an immediate mode system. A retain mode system, instead, at the beginning during setup, you describe all the things that you want the system to draw, and then it draws them. And so all those draw calls that you do in immediate mode are handled by the system for you. Examples are most game engines. If you've heard of Unreal Engine or the Torque engine or the Source engine, those are all high-level retain mode systems. In the web world, SVG, and even the HTML DOM is a retain mode. You describe the divs and the tables, and it decides to draw them for you. So why is that important? Well, if you look at a simple example, let's assume you want to move a sphere across the screen and have a static green rectangle. Well, in an immediate mode, you'd have a loop that looks something like this. You would start off the loop, and inside the loop, you would clear the screen. You would move your draw cursor, set the color to red, draw your circle. Move to where you want the green square, set the color to green, draw the square, and iterate through that loop. And even those calls to like draw circle and draw square, inside, they probably have another 5, 10, 15, maybe even 30 calls. And so per frame, that's a lot of calls. In retain mode, you create these things at setup time. So you create a circle and you set its color to red. You create a square and you set its color to green. Since the green one doesn't move, we can set the position outside the loop. And then inside the loop, you see all we do is we update the circle's position. And that means the part that gets executed often is very small. And that's why we chose retain mode. That being said, O3D is a very, very low-level API. So it's barely above OpenGL and D3. It's just enough to save you from having to make those calls. It's not like a lot of the higher-level scene graphs, and it's certainly not all the way up at the high-level game engines. And we did that to give you the most flexibility. We wanted it so that you could write any kind of application you wanted, but where we decided that JavaScript would probably be too slow, we implemented those parts in the plugin. If you've ever used a retain mode API before, they usually have something called a transform graph that have transforms and matrices and parents and children that describe how how the scene is laid out in 3D. And O3D has those as well. But O3D also has a new kind of graph called a render graph. And the render graph is what you do to tell O3D how to use the data in the transform graph to build your display, to draw what you see on the screen. I'm not going to go into the details. You can look them up in the documentation. But this is really what gives O3D its flexibility to do all the effects that you see in a modern game. So when you're programming with O3D, like I mentioned, it's very low level. If you're used to programming in GL at a low level, or you're used to programming in Direct3D, you'll find a lot of the things very similar. But for a lot of people, that's probably too low level. So we have written a bunch of JavaScript libraries that make many of those things easier. There are libraries for making primitives like a sphere or a box or a plane. There are libraries for building shaders for you, so you don't have to learn about shaders at the beginning. There are libraries for doing picking and libraries for loading and quite a few other things. And those aren't really part of O3D. They're just samples that we provide, but they're very powerful. They're great because they're good samples. You can look at them. They're all written in JavaScript. And because they're just JavaScript, you can change them. If you don't like the way it works and you need to change it a little, it's right there. You can change it. And then finally, we're hoping that over time, higher level libraries are written. So what I mean by that is, like, for example, JavaScript is relatively hard to do DOM manipulation, but we have libraries like jQuery that make it very easy. Or Python might be hard for making web pages, but we have There's Django for making that easy. And so hopefully someday Google or maybe some of you will write frameworks in JavaScript that wrap O3D and provide higher level functionality. A typical O3D application is obviously split into assets and code. Code is what you'd see in a normal JavaScript application. You set up your web page, you set up your JavaScript, you set up event handlers to read the keyboard and the mouse. Assets, you have basically two paths. You can either call functions to build your assets, like building a sphere or building a box, or you can load them. And so loading assets in O3D, one thing we want to make very clear is that O3D does not have a file format. So even our samples, you see them load files. Those files are just samples. Instead, O3D implements a zipped system, zipped archive system. So what you do is you zip up all your files. We actually support something called gzipped tar files. And inside, you can put text files. The most obvious example is a JSON file. But you can also put comma-separated values or XML. You put your textures, and then we have a few things that we store in binary, things like vertex data, the animation data, and skinning data, because we thought that those would be a little bit too big to put in text, although you're free to put them in text. And then we provide APIs for you to load that archive from the net and then look into it and use all the pieces you find in to rebuild your scene. And the advantage to that over a fixed function is that it provides a lot more flexibility. If you want to make your own format that just has a few things like lines and their widths and colors, you can do that. If you want to do a format that's got collision data and hit points for a character, you can do that. So anything you want to put in there, it's up to you. So that said, even though O3D itself doesn't provide a format, we've provided a sample that makes a format for you. And that sample uses Collada. And so because it uses Collada, you can use almost any 3D modeling package if it exports Collada, save out a Collada file, run it through our converter at the command line, and it will give you a zipped archive file that you can use with our samples in O3D. So you can very quickly get something on the screen. So I'm going to go over the few steps to make a small game. Hopefully I won't run out of time. And show you how to make a small game in O3D. And so like I mentioned before, O3D is all web-based. So the first thing you're going to want to do is get our utility libraries in, assuming you want to use them. And so here you can see that we load this base JS file. And that base JS file includes a system for loading other modules. And so you can see below that we include the utility module and the math module, and we could include some more. And then below that you see the body tag like you'd see in any HTML. And we're setting up the onload to call a function called init when the page is loaded. And below that you see a div. And O3D being a plugin, normally you would use an object tag to load a plugin. And you can do that too. There's nothing stopping you. But what we did is we found that the object tags have issues. Some browsers want them different than others. And so it was easier, we thought, just to write a utility library that would scan your document for divs with an ID that start with O3D and then insert a O3D object inside there. And that way it works across browser. So if you go in here, you'll see that here's our init function that's going to get called when the page loads. And it's going to call the utility function that I just mentioned, called makeClients. And that's, like I said, it's going to search through all the divs, and it's going to insert a O3D area inside there. And it's asynchronous. It's asynchronous because some browsers have some issues. When you ask them to create something like a plugin, they may take a few moments to do it. And so to make that cross-browser, we have that asynchronous. And so you pass in the function that you want to call. Here we're saying call init step 2. And so you can see right below, here is init step 2. And it gets passed the elements that got created. And since in the sample we're only going to create one element, I just pull that element directly out. Then below that, we're pulling out some globals. So this gmath is just to have a shorter way of referencing the math library. And this gclient, that is the base of O3D. From that object is where all the O3D APIs exist. Below that, we create a pack. And a pack is something that is used to manage the lifetime of the things that live inside O3D, things like textures and vertices. If you're familiar with things that are reference counted, a pack just holds one reference count to an object. If you remove something from a pack, then that releases that reference count. And if that's the last thing that's referencing it, it will disappear. The next line, we're creating a root transform, or we're creating a transform and storing it in a variable called root. And that's, like I mentioned before, it's part of the transform graph. And then finally, we have a utility function to set up a render graph for you. And a few slides ago, I showed you a render graph. You're free to make your own, and you can create all the objects you saw there by hand. But it turns out that for quite a few apps, there's a very common setup that will handle a lot of cases. And so we call that function. It creates all those objects, and it returns this object that we're storing in view info that has references to all the things it created so that you can use them later. We pass in the root to tell it that the render graph it's creating to render the tree that starts at this root. So then we have to set up a camera. If you guys are familiar with GL or DirectX, this will be familiar. If you're not, well, bear with me. Up here we have a variable that's holding the position of the person viewing the scene. Where they're looking is the target, and the direction that's up. And at the bottom, in update camera, you can see that we're calling this function lookAt, and it's going to create a matrix, and we're storing that matrix in an object that was created for us in that view info to set the view matrix that the system uses. Above, you can see where we're creating a projection matrix. And this perspective function is just like the one you find in GL. You set up the field of view and the aspect ratio of the area, and we're setting it in one of those objects in the render graph. And so if I show you that example, we'll load it up here. You're just going to get a gray screen because we haven't really put anything on the screen yet. So that's the next step. Let's put something on the screen. So the first thing we're going to do is we're going to create a basic material. And this is another one of those utility functions that's hiding a lot of the things under the hood. If you actually did it in the low-level O3D, you have to create shaders, and you have to set up quite a few things. But our high-level libraries will do this for you. And so this is a green material, just solid green. Then here we're calling a different utility function. This one creates a shader for us by loading it from a file. And this shader does a checkerboard pattern. Next, we're calling this function called create and bind standard params. And for any of you who have done shaders before, you know that shaders require parameters. So we have a system, a way of providing those parameters, and we have a way of linking them so that you can provide parameters to many, many shaders in a global way. And so what this is doing is, since we wrote the utilities that made the shaders, we know what parameters they need, and we can return an object that will let you set some of those parameters in a global way. So you can see just below that, we're setting the light position and the light color for both of those materials in one place. The next step is to create a plane. This creates a plane 100 units by 100 units. And then we create a transform. We parent that transform to the root that we created before. And we add the shape we just created to get displayed at the position of that transform. Down below, we create a cylinder. We use the red material on the cylinder. And again, we're going to create another transform, parent the transform, and add the shape. And this time, we're storing that transform in a global called gPlayer transform so that we can manipulate it later. And so with those couple of lines, if I load the sample, we now have a plane and a cylinder. So that's fine, but we're making a game, so let's keep going. Let's let the user move something. So I think that most JavaScript apps probably look for a key press or a mouse click. But in a game, you want to know whether the key is down and when it's released. So in this case, we're going to set up some events for when a key is up and down. And then we're just going to store a global array, key down. And we're going to store for each code whether that key is up or down. That makes it easy to check. whether the user is holding or has released a key. And so we're going to go back to where we set up before, and at the very end of our setup, we're going to add a render callback. And a render callback is a function that will get called in JavaScript every time the system's about to render. And so for most LCD screens, that's probably 60 times a second. So here is our function onRender, and it gets passed a render event. And from that, we pull this value elapsed time. Elapsed time is the number of seconds since the last time it was rendered. So you can use that, and we'll show you how in the next step. And so finally, let's move something. Here we have all these if statements. On the left column, these are the values for looking at the cursor keys. On the right column, these are the values for looking at the A, S, W, and D keys, which many of you, if you're gamers, you'll be familiar with. And we set some direction variables. And then down here, we're just going to add the direction directly to the player's position. And you can see that we're updating the player transform that we'd created before. So if I show you that sample, we now have a cylinder moving, a little fast, a little jerky. So the next thing we want to do is we want to make that move frame rate independent. And we want to do that because some machines, like maybe your mother's machine or your grandmother's machine, are very slow. And then your machine is, of course, very fast. So you want to make it so that no matter what machine you're running your application on, it runs at the same relative speed. So to do that, we're going to set a constant called move velocity in units per second. And we're going to go back into our handle move keys function. And instead of using the direction directly, we're going to multiply that by our velocity and multiply that by our elapsed time. And that will give us a percentage of the number of units per second added to our position. And that will make it run smooth and run the same frame rate or the same relative movement on any machine. So if I show you that sample, you can see it's now moving a little smoother. It is slower, but that's because our velocity is slower. But you'll notice that there's a new problem. We're looking into the screen kind of at a diagonal way, but the cylinder is moving along the grid. So that's not very good. That's not very game-like. So let's fix that. Let's make it move relative to the camera. I'm not going to explain the math here, but the simple explanation is this function, compute move matrix from view matrix, takes the view matrix we made before in step 1, and it builds a matrix that we can use to do some math to make that movement screen camera relative. And so back in step 1, we had a function update camera where we were computing a view matrix. And here, we're going to call that function with the view matrix and store it in a global move matrix, and we put it in the update camera function so that no matter how the camera gets updated, that matrix will always be correct. So then we go back to where we were moving the player, and instead of using the velocity directly, we're going to use it in this function, use that move matrix, and it's going to return this value that we can use to move it camera relative. So if we do it now, you'll see it moves across the screen the way the camera's facing, and in and out. It's no longer on the grid. Now that we've done that, we can move the camera. So let's move the camera. It's very easy. Before, in step 1, we set up a global with the target position, and we're just going to update that global here with the player's position, and we're going to call update camera. We made this function move camera. We're going to add that to our onRender so that every frame the camera will aim at the player. And so with just that small change, now the camera follows the player. That's nice, but you can see it's kind of stiff. It's kind of hard to look at when a player moves like that. So let's smooth that movement out. So that's very easy. This is a trick many game programmers use. instead of taking the position and putting it directly, the target position, and put it directly in the target, we're just going to take a percentage of that and add it to the target. So here we're saying move 3% closer to the place we want to be. That's what this 3.03 on the end is. Move the target, the current target, 3% closer to the new target. Well, since it's running at 30 or 60 hertz, that's very quickly going to add up to point to the actual place we want to be. But it will make it nice and smooth. So we show you that sample. Now you'll see the camera is playing catch-up. So it doesn't bounce like it used to. It's a much better feeling, very much more like a professional game. So sliding around is nice, but that's only one step. We need to give the player something else to do. So let's add a little bit of action. This is a tiny bit complicated, but not too bad. First, we're going to check whether the player can jump, and I'll explain that at the end, why that's important. But this is just checking, did the player press the space bar? If he did, we're setting jump to true and can jump to false, so that he can't jump again. And then we're setting the player's velocity to throw him in the air. The next time it comes through here, we'll see that he is jumping. And so here we're going to add some gravity to the velocity so that he'll come back down from the air. And then here, just like the other positions, we're going to add the velocity in a frame-independent way to his vertical position. And then here we're just checking to see, did he hit the floor? Did he get back to 0? And if he did, we glue him to the floor, and we say he's no longer jumping. And then at the end, if he's not jumping, if he's finished jumping, this code down at the bottom basically says, did he let off the spacebar? Because otherwise he would hold the spacebar, and the character would just jump and jump and jump. And so this says that the user must let off the keyboard once before he can jump again. So if we show you that one, he now jumps. Okay, so let's spiff that up a little bit. Let's add an effect. So this is, again, using our utility library. We're going to create a particle system. And from that, we're going to create an emitter. And then the first thing we're going to do is we're going to say we want additive blending, which adds the colors as it creates particles. This part here is creating a color ramp, and it says fade from white at 30% opaque to white at 0% opaque, or 100% translucent. This part down here sets a bunch of parameters. So this says we want 30 particles. We want each particle to last half of a second. We want them to start 5 units big, grow to 10 units big, to spin. And then this function down here is a function we provide if we want to set any of those parameters different per particle. So in this case, this math here, it's creating a velocity along the ground in one direction and then spinning it 360 degrees to make the particles come out in a circle. And the acceleration at the bottom is going to make the particles slow down as they come out. And then at the bottom here, we create something called a one-shot, and that's for effects like explosions or poofs that just go one at a time. So we go back into where we were jumping, and when we hit the ground, we trigger a poof. And so if we go back, now we get a little poof when we jump. Okay, that's great, but this is programmer art. If you were going to do a real game, you would need real artists, and you need real art, not just a plane and a cylinder. So the next step is to load a character. This character is created in 3D Studio Max by some artists. They exported it to Collada. We ran the utility to build one of our sample formats. And here's the code to load it. So these first 2 lines are the same as they were before when we were making a cylinder. But now instead of making a cylinder, we're going to load a scene. So you can see here we call something called, we create another pack. You don't have to do that. You could pass in your own pack. But it's good for keeping things separate. It makes them easier to manage. And then we're calling this function load scene. We're passing in that pack to say everything that you load, create inside that pack. Everything that you load, parent to the player transform we created. Here is the URL for the file. And then finally, because it's a web API, it's going to take a few moments to download that file. And so this is an asynchronous function, and it's going to call this init step 3. And so we broke init step 2 into 2 parts. And so it continues here in init step 3. And we call this function prepare pack. Prepare pack will look at the assets that were just loaded and create standard shaders for you. If you were making a professional game, you would probably do this step yourself and make really fancy shaders. But this function creates basic shaders. And then like we did before, we're going to bind params. And this is so that any of the effects and shaders that just got created will share the same lighting parameters. And so if I show you that sample, we now have a character on the screen. Of course, now we have a new problem. He doesn't face the right way. A cylinder, of course, doesn't have a front, but a character does. So the next thing to do is orient the character. So here we're doing some math based on our translation, which way to point him. But we're going to do the same trick we did for the camera and smooth it out. And the reason is that character only has 4 directions. We only have 4 cursor keys. And you could have combinations that would give him 8 directions. And if we only just pointed him the direction, he would like face one way and just snap immediately to one side. So that's no good. So instead, you can see here, just like we did for the camera, we're just going to take the way we want to face, the way we are facing, and just add 20% toward the way we want to face each frame. And finally, we use that information to rotate the character. So if I show you that example, now you can see he's facing the right way. And of course, the next step is animation. So to animate, O3D animates in seconds, but artists usually animate in frames, and that's usually a setting in their 3D software. My artists animated in 3D Studio Max, and they told me that they used 30 Hertz frames. And they told me that there was an idle animation that started at frame 247, and it ended at frame 573. So I'm just storing those 2 constants here. And I'm making a global variable called animation timer, and we'll get to that in a moment. Where we loaded the character, now we're going to create a parameter object. And on that parameter object, we're going to create a float parameter, which is a number if you're used to JavaScript. And so we changed the load scene. We added one more option, which is we pass that parameter into the loader. And what that says is, any animation you find in the scene, make it controlled by this parameter. So having done that, once it's loaded, we added to our onRender a function called handle animation. And you can see here, we just take this anim timer variable, we add the elapsed time, so that's going to make the animation go forward. And when we get to the end time, we're going to go back to the start time. And this math here is just a fancy way of saying, go back to the start time. And then finally, we're going to take that value that we're using, and we're going to stuff it into our animation parameter. And that will control the animation. So now he's animated pretty quick. So the next step I don't have on the board. And the reason is, it was a few lines of code, maybe 60, 70 lines, but it's basically just this same loop. This one is handling idle. It's saying when you get to the end of idle, go back to the start of idle. So there's another piece of code that says when you get to the end of jump, go back to the beginning of jump, or when you get to the end of walk, go back to the end of walk. And has a few case statements and if statements to say, are you walking or are you jumping? And it was kind of messy, so I didn't put it up, but it's just basically this same thing repeated a couple of different times. If you're interested in the details, the sample is on our code site. You can download all these samples and use them, and you can do a difference on those two files and see what changed. But if I show you that sample, now he actually runs around, and if he jumps, we have a jump animation. And there's actually 4 idle animations, so he randomly will pick something else to do. So the last step is to load a background. And it's basically the exact same step as the step to load a character. But because loading 2 scenes, and they're both asynchronous, is harder than loading 1 scene. If you just use the previous function, you'd have to chain them. You'd have to load the first scene. When it finishes, it goes to step 3. Step 3 loads another scene, and when it finishes, it goes to step 4. Instead, we have another thing in our utility library called a loader. And what a loader does is it lets you ask for a whole bunch of things to be loaded, and it'll give you a callback when they're all finished. So in this line, we create a loader, and we say, when everything this loader is using is finished, call this function in its step 3. This next part is just the same code we had before to load the character, except it's using the loader to do the loading. And here is pretty much that same code repeated, except that we're actually loading a background scene instead of the character. And you can see that whereas these used to call in its step 3, now they call prepare scene. So both of these call prepare scene, the other one is down here. And prepare scene is just below. They each prepare their own pack, all the things that just got loaded for them. They each bind their parameters for the lighting, and they each add themselves to the transform graph. And there we have it. We have our little game with a scene loaded in about 20 minutes. So if you take that to its logical conclusion, this is an example of a game that a company outside of Google called Large Animal Games. They made this. They had no JavaScript experience before, and they had no O3D experience, and they put this together in about 5 weeks. And it's already up on their website. I don't think it's 100% finished, but they even made it so that you can edit levels inside the game. Hopefully it will start soon. There it goes. So this is basically the same principles that you saw, and here's a little game. And with level editing and collectibles, here's some little things to collect. When you collect them, then you plant them. But if you plant them, this little guy will come and eat them. And so one thing I want to make clear, I mentioned before that O3D is not just about 3D. I mean, it's just not just about games. It's about any kind of 3D you want to do or any kind of display. So here's a small sample I threw together a few months ago. This is a windowing system built with O3D. The blue area is just one O3D area, and then JavaScript is controlling the render graph to make these different windows, and each have them a different area. And we can open a few more, stretch them or close them. But you can see that because we didn't make a specific system and we stayed very low level, O3D is very, very flexible. And so you can use it for whatever you want to use it for, 2D, 3D, games or not games, all those things are possible. So that's basically it. The O3D is on this, is available there. You can see it. It's open source. You can look at all the source. You can contribute. And if you have any questions, I will, 頑張って日本語で大丈夫だと思いますけど。質問がありますか?
Besides graphics, do you have any plans to support physics or audio capabilities?
Well, the question was, do we have any plans to support audio or physics? For physics, we do have some samples that show doing physics in JavaScript. There's a JavaScript API called Box2D, and we have a sample showing that. I don't think I have it up right now. But In the future, we also have another technology called native client, which lets you run C++ in the browser. And hopefully at some point in the near future, those will be connected. And for things like physics, you'll be able to do that. For sound, right now, you can use the sound tag from HTML5, or you can use Flash for sound. There's probably some sound things in the works, but we don't have anything to announce at this time. Anybody else? No? Okay, well then. Oh, up there.
I was wondering, what's this actually based on? I mean, is this based on OpenGL, like on the level below?
Right. So the question is, what is O3D based on? It's based on both OpenGL and DirectX. And the reason we did that is that on Windows, there's a lot of machines that have really poor OpenGL support. And so by going with DirectX and providing this layer on top of it, we were able to get the best performance on the most machines. So on Windows, it's DirectX. On GL, on OS X and Linux, it's GL. Also, if you download the source, you can compile a GL version for Windows, but we're not shipping that. But it is available. Anybody else? We have time for one more? Up there.
ネイティブクライアントとO3D の使い分けはどのような場面でどっちを使うっていう使い分けはどのようにすればいいでしょうか。
ちょっと分かりにくかったんですけど、It's probably easiest if you come ask me after. Because I could ask you to say it again a little bit. My Japanese probably isn't up to that level. I heard something about dividing it, or how do you divide the something, but I couldn't understand it all. I'm sorry. One more? No? Okay. All right. Thank you very much. Please come out to the lobby, and I'll answer any questions you have. I have to actually go to a couple of meetings after this, but after 4:30, I'll be around. And I'm happy to answer any questions. And one-on-one, it's much easier to do Japanese, so please come out. All right, thank you.